All right, we just changed our microphone. So like I said, in your chat right now, there's a link to a Google form. This is so that I can provide you the interactive 3D CAD files of the builds. It's a little bit easier than step-by-step instructions. It'll have a bill of materials with it. In addition to that, you'll be able to turn components on, turn components off, and see what components went on our sample build and our sample assembly. So like I said, I'm going to run a little bit of a review and a talk this morning about how to build things and put things together. Then we're going to send you that interactive 3D CAD file, and you will build your robot base this morning. We're going to be here to help you, as I said. So if there are any questions, you can put them in the chat, all right, as you go forward for this session. It'll be the same thing on Thursday. We're going to do an A-frame. We're going to do some mechanisms. You may not get all of the mechanisms built on Thursday, but the idea is to take you through some of the small basic stuff and see how it all goes together into a big assembly and a frame. And then on next week, we're going to start and go back and cover all of the programming and setting up your software for the programming and so on. All right. So if you're not going to do hardware build yourself, you can follow along and watch. We are recording these, and once they're cleaned up and edited, they will be posted to the Studica Robotics YouTube channel. So you will have access to that information. And as I also said, when you fill in that link for me, you will get the interactive 3D PDF build instructions for the robot as well. All right. All right. So the intent behind this was to build a base robot. This base robot we've been working on just to test different mechanisms and to allow us to decide certain things going forward. This base robot can be used for the waste management challenge, if you wish, which is our challenge, our interactive online challenge, and the challenge that we encourage you to do to train for World Skills Shanghai. Okay. Somebody's asking where the Google form is, and you should see that link. So if you click on that link, you should be able to get that. All right. So James is going to post that again. If people are having trouble with that link, just let me know, and we'll make sure that it comes in. I don't have it open right now, so I don't know if anybody's successfully got in there, but we'll double check that going forward when we take a little bit of a break. Okay. Actually, I'll stop sharing my screen. I'll tell you what, and I'll let James share his, and he can just show you what that form looks like. So it's simple. It's just so that we can send you some information. All right. Today, once we get a little bit of a rest for the interactive 3D PDF files. Okay.
Can you share me?
Yeah, I'm going to. All right, so we're going to do a robot base build today. We're going to talk about a few things first when working with the build system. So some of the things we're going to cover are, I'm going to start with getting ready for the build, some tips and tricks on what you need to put things together, maybe some tools that you want to have and so on handy. This will help you think about what you may want to put in your toolbox when going to a competition or so on when you do that. We're going to talk a little bit about the design concept. There's lots of different designs that you can do, and that's entirely up to you. It's your choice We picked a certain design concept for this one just because of the algorithms and the theory behind it. We'll talk about organizing the build, how to keep your stuff together, separated and organized. All right. And as I said, we built a basic robot, which is just created as a resource for you. If you're looking for a little bit of a step-by-step instructional guide, okay, on how to build a basic chassis and how the structure of a robot would be put together and programmed. Right. So that's what we're going to cover today. Talk a little bit about some basic tools that you will require. So in your collection, you'll have a set of Allen keys. There are 4 sizes that are a must that you're going to need. The 1.5 millimeter, the 2 millimeter, the 2.5 millimeter, and the 5 millimeter. Okay. So you will have your Allen key set. We'll go over a few tools, and they will be in there for you to work through and do that. So 1.5 millimeter is used for the set screws. The 2 millimeter is for your button-headed screws. The 2.5 millimeter is for your socket-headed cap screws. And we are going to use the 5 millimeter when we're putting together our wheels. So for our large socket-headed cap screws. There is a 5.5 millimeter combination wrench that you can use. You may want to find one that's longer, and I'll talk about that, but those basic tools are included. There's a 2.5 millimeter ball head driver. So we have a picture of that there. That's kind of handy. And you may want a larger 5 millimeter T drive or maybe some T drives. And when we switch back, we can talk about that. So when I start to put together some frames and so on, I'll show you some of these tools that we go for that you would think about having in your collection. Okay. Some of the other things that you may want, and I'll show you these, is needle nose pliers. These are kind of handy and they're easy. Everybody can get needle nose pliers just to reach into to certain locations. If you are going to adjust the wiring on your robot, you may wish to have a power pole crimper and some power poles. Okay, so those tools are easily available. We have them for you. You can get them online or add them to your kit. You may wish to change some of your cables, so you can do custom PWM crimping. So we keep a PWM crimp tool here just in case we want to make longer or shorter cables. And, I may use, I may not use, I've got a little picture of a sample vise there that clamps onto the edge of a table. As James said earlier, if you're going to an event and you're allowed one toolbox, that can take up space. So that's something that you have to think about whether you want to bring it to an event. But, locally or handy around, you can have those, and there's just a sample one. I use a little one that's got a slide on it that clamps to the side of the table that I'm working on. Remember that when you do go to an event itself, there are some tools provided, yes, and you'll have a list of those, and there would be vices and so on. But sometimes when you're trying to assemble certain mechanisms and you only got 2 hands, it's kind of handy to have that extra hand going forward, okay, when you're going to look at it. All right. So today we're going to look at a chassis. Some people would call it the base. Some people will call that the drive system. And one thing that you must remember about your chassis is that it's generally more important than anything else in the robot. Okay. If that base chassis isn't successful, then your robot is not going to drive. So this is where we start. We start with this. We go through the design iterations. Okay, what type of chassis do we want? What type of weight does the chassis have to support, right? What drive system are we using? We may have obstacles to go over. We may have height restrictions and drive restrictions. And you also have to think about when you are designing your chassis, okay, exactly what your programming skills are. So we cannot provide to you all of the resources. So with a lot of these different chassis, there's a little bit of extra math and a little bit of extra theory when you're going to put them together. Your chassis needs, of course, to meet your strategy goals. So when you get a challenge to start with, the first thing you want to do is sit down with that challenge and do a strategical analysis, right? I usually tell people when we're doing this to start, look at all the tasks that you need to complete and begin to do two things well, all right? And work towards doing those two things well. Once you do those two things well, then after that, you can begin to redevelop and work onto it. But a lot of times it can be difficult if you try to do too much at once. You want to make sure that what you're going to build in your chassis can be done with the resources that you have available, right? So, you know, what we're going to do, we can build this chassis basically with exactly what's in the collection, okay, using the two tools that come in the collection. You know, don't build something that requires a special component or part or something that's been 3D printed that may break, that you do not have any more of or do not have a supply of. Right? Make sure that your chassis doesn't need a lot of maintenance, and we'll talk about that. Make sure you can easily fix it. I put fix in 4 minutes. I always change this number because I tell people that if something breaks, it's going to break 4 or 5 minutes before you're going to compete in a competition or do a test run or do a sample run. So you want to make sure that your chassis can be fixed easily and quickly. And the last thing about that chassis, once again, it is that it is more important than anything else on the robot. All right. So when you go to build it and you sit down, the first thing that we wanted to do was look at this and look at some of the constraints of the challenge. Right? So as an example, is there a size constraint on the field that would limit the size of the robot? Okay. Most of the challenges in World Skills do have a size constraint, whether it be an opening that you have to go through, whether it be a maneuverability section, okay? There could be an obstacle that gets added in the way, things like that. So you have to look at that and say, okay, when I'm gonna build my chassis, what size constraint do I wanna put on that, right? Does the robot need to drive up a ramp, or are there objects there? What about the traction? Okay, we need to look at that. So we know that when we look at different chassis, and if you've been in some of our other sessions, we've talked about 4-wheel drive chassis. We've talked about chassis that only have 2 motors driving them as opposed to 4 motors driving them. We've talked about mechanism and so on. So a lot of this we have to think about going forward on what court am I on, what obstacles are there, what designs on the court, and what best suits it. So our biggest thing here is for us is generally about traction, okay, going forward. Is weight an issue? So sometimes your robot may need to lift itself, it may need to lift objects, okay? Do you need to minimize weight? Okay, do you need to adjust weight? Right? Because remember that your center of gravity of the robot is very, very important. If we're using mechanism, or what we're going to do today is what can be called a Kiwi drive or a holomic drive, we need to ensure that there's proper weight balance on that robot. Okay. Do we have a restriction that, you know, the robot needs to be lighter? So these are things you need to look at when you are going to do your challenge. There also has to be consistency in autonomous movement and control, right? So this goes back to the balance, right, when you are moving. This goes back to the fact that do you have a ramp or not a ramp on the court that you must travel up? Because you need to have a consistent autonomous movement and control, especially if you're coding things like your PID, okay? So that you can get a nice smooth drive, you're ramping up, you're ramping down, and so on. So there has to be consistency in that autonomous movement based upon where you're located, based upon the surface, based upon the weight distribution at any particular time of the robot, right? And please remember that great prototyping is what you need to do. You should experiment with all sorts of different designs. Think on the floor behind us right now, there's 3 or 4 different designs, okay? We've built all sorts of different kinds, and we've just prototyped them, and then we sit and we say, okay, these are the performance characteristics of what we built here. It's best suited for this challenge. These are the performance characteristics of XX or YY. And this is what we do going forward through that challenge. Okay. So the drive base. So our drive base that we are going to build is going to be a Kiwi drive, okay, or a 3-wheel holonomic drive. It'll have 3 omnidirectional wheels and DC motors. So we're going to use 3 DC motors on it to drive the wheels. Okay. Why did we choose it? Simply because it is an interesting chassis to build, right? So that we can take a look at a little bit of the programming algorithms when you are going to do this type of a chassis. For those of you that haven't built one, it is not the easiest chassis to build and program. Okay, there are a lot of issues. There's math involved. There's weight distribution involved. Okay, there's lack of traction involved when you only have 3 wheels, vice 4 wheels, and so on. But you know, we thought we would build this chassis in this training because we've built some other chassis in different training going forward, right? They're you know, becoming a little bit sought after. We see a lot of personal service robots right now out there that have 3 wheels, okay, so that you can do that. It gives you a little bit of greater maneuverability, okay. But remember, as I said, it comes at the expense of some complex algorithms and so on required to program it. Okay. A robot like this, which has 3 motorized wheels, can have fairly independent tangential, normal, and angular velocities. Okay. It can be mechanically simpler as a robot, but remember that a robot with 4 wheels will have more acceleration with the same kind of motors. So these are little trade-offs that you've got. The 4-wheel drive robot will be better if you're looking for floor traction, okay, because there's less wheel slippage. This simply has to do with coefficient of friction and the pressure against the floor equally for all of the wheels, okay. So our 3-wheel drive robot chassis we're going to build using our Omni wheels. So it will be capable in moving of any direction by changing the velocity and direction of each wheel without changing the wheel orientation. So how is this possible? James and I looked at this and thought about how much math and theory we would actually put into this so that you can see it. This is what I call the simple explanation, if you want to look at it. So basically your vectoring movement is achieved through the sum of forces generated by each wheel, all right? So in simple, you'll see that in order to move the motor in one direction, motor A has to move in the negative direction, okay? And motor B would have to move, or motor B and C in a positive direction, okay? So this is a simple diagram. It shows you how each motor has to move with different power. So not only is a motor changing direction to move in to move the robot in a different way, you're also adjusting the power on each motor when you're going to try to negate different forces, okay? So that is a very, very simple explanation on a vector diagram of this type of movement, okay? So somebody had just asked the question, is this a holonomic or a non-holonomic? So basically this is a holonomic omnidirectional mobile robot, okay? This is a little bit of an explanation of the theory behind it a little more, okay? So it covers the occupied robot space, okay? There has to be an omnidirectional motion method in geometry that gets figured out, okay? So that the robot can move in any direction, irrespective of its position and orientation, all right? So there are some calculations that are required. We did not want to bore you with all of the different calculations. I will share the paper that I've got here from the Journal of Robotics and Control. I picked one of the newer ones that I found, and this will talk you through the theory about how to set up a 3-wheel drive holonomic robot, about vectoring and about different motor velocities that are required to move in certain directions. It provides not bad little chart in there about speeds of each motor at each time based upon things. And there are other resources that are available. And I'm quite sure that if a lot of you are in a robotics program, a lot of this theory is taught to you in the classroom going forward. All right. Whoops. Okay. So that's there. What we'll do is when I check the responses and send you out the 3D PDF file, we'll also send you out this wonderful document. In fact, what I'll do is I'll bring it up in a second. Let me just stop sharing here. And what we'll do is we'll go back and I'll just take you through that. Oh, maybe not. All right, I will send it. I don't have it right now. I thought I did right here going forward. So I'll make sure that everybody gets that link going forward as we go out. But if you actually Google it, just cut and paste that out, you'll be able to find that link. It's a very, very good job by some students to put that together. All right. All right, let's click back over. Having to switch back. All right, there we go. Okay. All right. So for this build, we are going to need the following. This is the bill of materials for it. Like I said, what we'll do is we'll send you out the interactive CAD file. We'll email that out to everybody on our break, and it will have the bill of materials in it. It's very simple. We're going to use 3 288 millimeter U channel, 6 120-degree brackets, 3 48 millimeter U channel, 3 motor mount plates, 3 Maverick DC gear motors. We're going to use our 3 Omni wheels. And there will be the total of the following nuts and bolts required. So there will be M3 by 12 millimeter socket-headed cap screws. You'll need 51 of them. M3 nylock nuts, 51. And we're going to talk about the nylock nuts in a minute. We put nylock in here because we designed this as the theory, as if you were going to do your final build. And I'll talk more about it in a minute. If you're just participating in this and you are going to disassemble this and take it apart again, you'll probably want to use 51 KEP nuts. But like I said, this was our final design, and I'll talk more about it in a second. And you're going to need 30 M3 by 10 millimeter button-headed cap screws. Now, do not get in the chat when I change the slide and go, oh, I need that, because you don't. We're going to send you that interactive PDF file when you get into your building. Okay, and all of this list will be there for you to get ready and to put together. And it's easily referenced by the part numbers that are required. All right. So this is what we are going to build our base chassis from. All right. So I will talk about the mechanical hardware for you to get started. So this is the explanation about the nylock nuts and the KEP nuts. So the nylock nuts basically have a nylon insert on them, okay? What that does is it allows the nut to grip a little bit better and it holds it. What does happen is they're a little bit harder to thread on and they're a little bit harder to unthread. And after the use of 3 or 4 times, okay, the nylon insert on the inside basically wears out and you lose the effectiveness of the nylock nut, okay? So if you are going to do assembly and disassembly a lot in your development, then during your development phase, you should use those KEP nuts, okay? So use the KEP nuts for now, and then once the design is finalized, for critical joints that do not need to move, you can use the nylon insert nuts, right? So just a little bit of a blurb on assembling your mechanical hardware for different mechanical joints and so on. Okay, so we needed to look at our base design for our triangle base. We had a few design considerations with it. So this is good for a flat surface. It's very, very good to navigate in a tight space, okay? And when we look at a tight space, here I put down a domestic environment. So we don't take a lot of space, easy to spin around, easy to move through a door, easy to move through an opening, okay? Narrow hallways, for instance, if it was a real industrial robot, would work well, okay? Due to their high center of gravity, because generally what happens is any mechanism that you design, it goes straight up the center of the robot and it has a high center of gravity. They have stability problems when they're moving on a ramp, okay? So as they begin to move on a ramp, they can tip left or right. Each wheel in this design needs to be 120 degrees apart, and the wheels need to be perfectly perpendicular to the center axis. If they are not, you're going to run into problems. Your frame must also be properly aligned. So we'll talk a little bit about this when I take you through some of the steps to put your frame together, okay? But it does need to be aligned correctly, and your wheels do need to be perpendicular, okay? Otherwise, your vectoring math is not going to work, and your robot is going to drift and not properly move in different directions. So as I said, it is not the simplest or easiest robot to build, okay? We're going to build the frame in a couple of sections. So the first thing that we're going to do is we're going to build and align the basic frame. So when we build and align the basic frame, what's important for you to look at here is that we're going to use the 288 millimeter channel. We are going to use the 120 degree brackets. And what's very important for you to realize is that the way that this was designed for the motor mounting is that on the top side, we are using 4 of the M12 socket-headed cap screws and nuts right here. But on the bottom side, you'll notice that we're only using 3, okay? And the reason is that we are going to mount the 48 millimeter U channel here with the motor mounts, okay, in order to put this frame together. So if we had that extra socket-headed cap screw in here right now, okay, what it would do is it would get in the way of us when we wanted to do that next stage for the mounting, all right? So I'm just going to stop sharing my screen, and we're going to switch over the cameras. All right. So I'm going to move that vise. So basically, we're going to start with the 288 channel when you're going to build your frame when you get your time, all right? So the channel, the mount, the flats, the motor mounts and everything in the collection, they have a hole pattern with it that's easy to align and put together, okay? So we can start by putting our frame together, all right, as we go through, and you'll notice that we do have our 120 degree mount that we are going to use with that frame. We are going to put a mount on the top, and you're going to put a mount on the bottom of your frame as you go forward, all right, when you find that, okay? Remember that what I said was there's going to be 4 of the 12 millimeter socket-headed cap screws right here, okay, that you'll use on the top, okay? So when you're going to put a frame on a mount, okay, this way. Oh, hang on. There we go. All right, there we go. When you're going to put a frame on the top of the mount, you're going to use 4 screws in the top, okay, so that you can see that and put that in. And then you're going to want to make sure that everything is properly aligned. We talked before about the fact that when you put a frame together, do not tighten everything up completely. You're going to put your socket-headed cap screws in. You're going to have some movement here, because then you are going to have to make sure that this is properly aligned so that when you put the motor mounts on, they are perpendicular to the center, okay? There's a lot of different ways that you can do this as well. I have this little guide that I got from my toolbox, okay? And with that little guide, as I'm putting together the frame, I can line that up, okay? So that I can ensure that I am perfectly straight at 120 degrees, okay? So that you can put things together, all right? What you want to do is you want to make sure that you're following the instructions that you've got in your 3D PDF file. Okay, so as you see that you are going to put that together, right? We can see that there's the way that I'm going to do my bracket. Okay, this bracket is going to go up, and then I can use my guide to make sure that everything is properly aligned. Yeah, I got it. So we could do that. All right. So just little things for you to look at to make sure that that everything is together. But this is going to be the first part of your build as you go forward. And like I said, we're going to take a break. We're going to share it with you, and we're going to give you the time to put that frame together as you're going forward. All right. So that's exactly what you want to do when you put that together. Okay. All right. So you're going to lay it all out. And once you lay that all out, then you can get it together. You can use a guide to square it up, or you can use the edges of the lines to make sure that you're squared up, okay? But you want to make sure that everything is properly concentric and put together, okay? So we'll lay that out like that, and then if you want to measure it, you can measure it and put it all together, okay? Like I said, you'll put one bracket on the top with 4 screws, and then on the other side, there'll be another bracket underneath, and you'll put the 3 on there, okay? And the reason is that you will eventually put a 48-degree mount on there, okay, going forward for that basic chassis. All right. So you're going to align the basic frame. Once you build and align the basic train, you're going to add the 48 millimeter to it. Okay, so these are zoom in diagrams from the 3D PDF file, right, that you've got. So this is the way that we decided to build it for ease. We then add the 48 millimeter U channel to the frame. And once again, we have to align that. Okay, remember that when you put the socket-headed cap screws in, there is going to be play, right? So you need to make sure that these properly get aligned so that they're all perpendicular, right? Otherwise, the wheels will be out of alignment. They won't be properly 120 degrees apart from the center line of the motor. Right? So the next step in your build is to add the 48 millimeter U channel. That once again is done with the M3 by 12 millimeter socket-headed cap screws. Okay. Once you've done that, what you want to do, and I don't have all of them in this one, is we're going to mount the motors to the motor mount plates. So you'll mount your motors to your motor mount plates, and you'll use your M3 by 10 millimeter button-headed screws, okay? And you want to make sure, and I'll show you one in a minute that doesn't have all the screws in it, and one of the reasons why we put them all in it in a second, but then you're going to just mount your motors to your motor mount plate. Right? And then once you have your motors in your motor mount plate, then slide them into the 48 millimeter U channel, right? And with the 48 millimeter U channel, you'll then use the button-headed cap screws to affix that motor into that 48 millimeter U channel. All right. Put me back over. So if we take a look at this this motor, there's the Maverick DC motor. This one I still have a hub on it, okay, for the wheels. But your button-headed cap screws are going to go through. You can see with this one is I only have 4 in it right now, and you can see that I can actually move it, right? Because I want to make sure I use the maximum allowable so that when I tighten those up, right, that if one comes loose, I won't get any extra movement. Right? So I'm going to use 1, 2, 3, 4, 5, 6. We're going to use 6 on there going forward. Once those motors are mounted, then what we do in the build instruction is this is already on your robot frame. Okay, you're going to slide the motor in, right? And you'll affix this into the robot frame, okay, using 4 button-headed cap screws on the side. So you've got the CAD drawing. Everything is all there and ready to go. Excellent. Okay, So at the end of that, it's a fairly simple structure. This is what you're going to have, right? You'll have your triangle base. You'll have your motors mounted with no wheels on them so that you can see it. And you want to just, at this point, do another double check to make sure that everything is square and everything is properly aligned. So like I said, the center line of those motors have to be aligned at 120 degrees. And the center line of the motors also have to be perpendicular to the square face of the motor, right? And if you think about it, if not, what's going to happen is your wheels are going to be crooked and they're going to be out of alignment. Right? So it is very, very tricky to get this oriented correctly. If you find you get a little bit of movement when you drive the robot and it's not quite right, you might want to recheck that alignment. Like I said, you can make a jig, you can make a tool to help you with it. I just use a small compass protractor that I've got. I thought about making a laser for this, but I thought that was a little bit of overkill going forward, right? So what you'll do is you'll mount the motors on the frame. After that, what you want to do is you want to mount the Omni wheels, okay? And I'll talk a little bit about mounting the Omni wheels and the hubs going forward, just so that you could see it, all right? And what you've got on an Omni wheel when you do it is you've got a deep side to the Omni wheel, as we call it, and a what I call a non-deep side or a flat side, okay, when you work through it. And what you want to make sure with your Omni wheel, and I'll show you in a little second, is that you are assembling it correctly and using the right side so that you get less slippage going forward, all right, when you do it. So you can put those together. This is the way that they work. You can use a couple of different things with it, and I'll just swap the screen back over here. All right. So we use a universal hub mount on there. So the hub itself will have 2 set screws, okay, for the shaft on the motor. So there'll be 2 set screws in here. You'll see that. One goes against the flat on the 6mm shaft, and the other would go simply against the other motor shaft to provide some extra ability to lock that, all right? The motor, the wheel itself will then go onto the motor, right? When you're gonna work through it, and you're gonna see it. And what you wanna do is you wanna make sure that on the inside that you have a flat surface area. So when the top of this section here, okay, your hub goes, when you mount the wheel on there, you want to make sure that what you feel in here is no ridges, that it's all flat on the inside of the section. Because what's going to happen is you're going to take the round section, put that back into the hole, okay, and yeah, and then you're going to use the longer screw to put that together, all right, so that we could see it, all right. So we'll put it in, put that on the side. What? There, okay, so that you can see that. And I'm just gonna put that up here so that we can see how that goes together, right? And you want to double check. Okay. So I got it nice and flat in here. It's a pressure fit. Okay, that's going to happen. And then we're going to run the wheel forward. Now, a couple of tricks on this. Okay, and that is that as you begin to tighten this up, you got to be a bit of a bull because it is a pressure fit. Okay, that as you tighten it, the wheel can move on the motor. Okay, so it's not really tight. So you need to make sure that you can properly hold that wheel, and it's the same thing if we were using macadam wheels. Okay, and I'll use a 5mm key here, right? And I want to make sure that I'm properly holding that wheel so that I can tighten that. There's really no need to over tighten it. What we find is that people try to do it this way where they're not holding the wheel, okay? And the wheel starts to spin because it's not under power, right? As they're putting that together, and therefore they don't get enough of a friction fit on that hub. So it can come apart. So you want to make sure and, use somebody else if you're holding that wheel, right? I can hold mine at an angle and I could tighten that and it's pretty straight. We use on ours, and I put it on the PowerPoint presentation, blue Loctite, all right? So this is blue Loctite. There's different colors of Loctite. There's the actual name brand Loctite. This one's called Vibratite, which is a Loctite clone. There's red, green, blue, purple. Each one is for a different use, right? But the blue Loctite is what we call medium Loctite, and the blue Loctite is designed so that you can loosen off a screw, all right, and take it back out. So it has what we call medium thread lock. So it will keep things like your set screws in firm, okay? It'll reduce the slippage on a screw like this, but that blue Loctite also will enable me, if I need to get out and change that wheel, okay, to simply break the Loctite. If you use red Loctite, it's going to seize it right in there, and you're going to have all sorts of difficulty, okay, when you put that all together. Right? So that's the way that we are going to do that. We actually put the hubs onto the shafts first, right, and then do the set screws, and then the Omni wheel goes in with the nut, all right, and the plate, okay, to put that in. And like I said, we can do that. Why did we go to this system? We went to this system for a reason. We talked about it a lot, but this way, with the same hub, if I have a damaged wheel, it's a very quick fix to take a wheel off and put a new wheel back on, right? And it's only one screw, and away you go. So that's why we chose our Omni wheels and our Mecanum wheels to use this type of hub system, okay? All right. So just a bit, then what you're going to do on your chassis is you're going to mount those, okay? As I said, you're going to need to ensure you hold the wheel so that the round plate provides enough pressure on the wheel to do that. And I would suggest, and you don't need it now, but going forward, think about it. Find yourself some blue Loctite or some blue medium thread locker, okay? So that covers the basic design or build of the frame that we wanted to do today. We're going to start simple. We just have a question, where can I find the PDF instruction? Like I said, we're going to have a break. And if you filled in the Google Doc, we are going to email that out to you, okay, so that you have that PDF instruction going forward. The PDF instruction would also have the parts list so that you can take your time now to get that ready. And we want you to build that frame in this session. So we'll send that out, and we will be available to you back and forth to talk and answer questions and so on the frame so that you can see it. So why don't we take 10? Oh, James will show it. Okay, perfect. So let me stop the share. I gotta check my Google Drive to see how many people.
So here we have the 3D PDF.
Oh, perfect.
So you can view the actual parts here. And then at the bottom is the parts list, even though you should be able to see it from the drawing. What's nice with the PDF is you can go into the tree and then take parts apart and choose what you want and what you don't want in the drawing. So if I uncheck everything, I can start checking stuff to see what is required and how to assemble and build it. You can zoom out, you can zoom in, and it allows you to build the robot without needing CAD software to open a step file or anything to see how it's assembled.
Right. So you're going to have the toolbar across the top, right? If you go down in, you'll see that it pops up as you move the cursor over it. If you do go into the section where the CAD file is, if you right click, I think, right click right there. Okay, you will get a pop down option. So with that pop down option, if you lose your model tree or whatever, just take your cursor and right click in there and you'll be able to look at that. You could also, if you wanted to, for instance, go to full screen multimedia right now, okay, which will allow you to go to full screen, right? Are you actually sharing that? I don't think we see the share. Oh, yeah, we do. Okay. So if you can go to the full screen and you can rotate that around. If you click on an object, for instance, okay, it'll highlight that object. And if you right click right now and anywhere, James, okay, with this, you could go back out and end that and also look at that 3D modeling tree as well. Okay. So you can isolate parts, view parts, and have a look at that tree. And that modeling tree, when you have that up, will give you exactly what part is what and how it goes together. So you'll be able to zoom in. It's interactive and have a look at it as you go forward. All right. So we have I have 36 attendees right now, and on my responses I have 32. Okay. So hopefully we're going to send that out and everybody's going to get it. If you are missing it, you haven't filled that in, let me know. I'm going to wait about 3 or 4 more minutes before we start to send this out to you. So if you have your robot kit, what I would do right now is get everything that we talked about together and ready to go. And we'll send this out in a few minutes because I see 37 and I'm still at 32. So, you know, maybe some of you are duplicated. That's no problem. But you can always just send your email in the chat, okay, as you go forward and have a look at it, okay? All right, so we'll just, and if there's problems, like I said, we'll be here interactively and we'll talk to you one-on-one and we'll make sure that, that we get everything built and ready for the frame going forward. All right, so James is, I still got responses here. All right. Okay, you might as well just give us a quick mute. We're live. Okay. So a couple of points for housekeeping because we had a few questions in the chat. I had emailed the interactive PDF. I'm just going to go over that with you. I then emailed that theory document on the holonomic drive. Some interesting reading on that and the way that you do it. When we get to coding next week, we're actually, I think James, because he's smarter than everybody else, we call him smarter than the average bear around here. He did it a little bit of a different way, using a different theory. Okay, so there's a lot of things that you can do. And I also emailed you because in case you wanted it, I emailed you the bill of materials for this section of the build in Microsoft Excel as well. I'm just going to share my screen and open up the interactive PDF. Okay. So I've just got everything that I used as a reference for today inside one folder as an example. And I'm going to just double click on the drive base. Right, it'll open up. So a couple of things are going to happen, and I'm not. Is it coming?
Are you?
we're going to see.
You're
So
not sharing your screen. You're sharing.
I don't know, it flipped over. Just hold on here.
Like new share.
Yeah, let me get to a new share.
That not.
This one. There we go. Okay. All right. A couple of things can happen. So number one, what happens here is it can't find the Arial Unicode MS font. It's just
That's because Windows doesn't include it anymore.
right. So Windows doesn't include that anymore. So if you just click OK, you're going to get that. Right. But what can happen when you bring that up is you'll see that I have a yellow bar there that talks about 3D and multimedia content has been enabled. Enable this feature if you trust this document, okay? And this is just because they don't want people sending bad things out in the world. So if you get that, what you got to do is you have to trust this document. Now, I'll tell you one thing on my system, I hit trust this document always. And every time I open this document, I have to actually trust it. So when you hit trust this document, okay, it'll pop up. At this point in time, I have 2 pages. One is the bill of materials. Okay. It'll take a bit of time to load. And one is that interactive 3DF PDF file that's there. Take a little time to play with this and get used to this. This comes out of a SolidWorks file. So down the left-hand side, you'll notice that I have some options, okay, for the toolbar so that we can spin, rotate, pan, change the camera properties. We can measure distance if we want, all right? You may or may not have some views in here, okay? So that view is the base view for drive base. If I sent you the one I play with, I actually went in as I was building this and I turned objects on and off and I created multiple views for myself. So I have a view called 48 millimeter only. I have a view called base only and so on, all right? You click on that hierarchical tree, all right? And open that up from your default view and you'll see all the component parts that are there so that you can scroll back and scroll up. And when you want to mess around with this, you can create your own views by turning objects on and off, okay, as you go through, right? If you hide the tree, you can do that. And there's other options here for you to change the view that you want to look at it or the illustration or so on, okay, as you go through, all right? If you want to cross-section it, you can. What I do a lot of times is I just go into the full screen multimedia mode, right? And then I can just interactively rotate that view in, have a look at the way that something is put together, okay, rotate that and view that out a little bit as we look at it. Okay. So you can work through that in that interactive PDF, all right? So there, just wanted to go over that. If you have any problems, just chat that. I know a couple of people had some issues opening things up. All right, you want to show this robot? Okay, so I'm going to try to move this closer. I'm so quick that during the break, I built this. All right, pretty quick. So overall, this is what we are going to end up building. We thought we'd start slow today, and we are going to build it in subsystems. So the drive base that you're putting together, you'll see is here. We're going to leave that open right there so that you can see the way that the 122 brackets are put together. You'll see that the 4 screws are on the top, and there are the 1, 2, 3 on the bottom, or 1, 2, 3, and then you have that 48 mount, okay, that's there underneath for that base frame structure, and it's squared up, okay? We will then build the A-frame and the tower mechanism that we see on this a little bit later in the week as we get going. So we'll probably send these to you ahead of time, and we'll talk about the different mechanisms and so on that you will be done. So we'll probably, in preparation for Thursday, now that I have it, I'll email out everybody the bill of materials so that you can at least get the parts together as we go forward. And then we'll begin to talk about the orientation of this robot and why certain things are in a certain direction and so on, okay? Including why we mounted the Titan the way that we did. So we have our Titan, okay, mounted at the back, and why we mounted the VMX the way that it is. Little trick, we talked about center of gravity. Remember that it's got the IMU in it. So you'll notice how it's mounted in the center of the robot. Okay, and you'll also notice how we've mounted it. And we'll talk about this with the Studica logo at the front of the robot. So this is the front of the robot, and that's so that we get the correct default orientation for the IMU. It also is very, very easily for me to get at right now. Okay, if I need to change a cable or adjust a cable, very, very simple. And it would be the same thing if I look back at the Titan. Okay, nice and easy to get at, clean wiring, and ready to go and to put together. Okay, so that you can see it. So we're going to leave that up as well, just so that you can get an idea of the frame, and you can see the way that these brackets are mounted on. And all you're going to do is just build that standard frame and get everything mounted up. We left a lot of time for this today because for many people, it might be their first time with the build system to put all that together. So, you know, we got lots of time for you to work at this. And if there's any questions on that build, just please let us know right away. If anybody didn't get the instructions because they didn't get registered up, please just put your email in the chat and we'll send them out to you. There's no problem to add you to the list. Questions? Okay, I hope everybody is building. We didn't get much raise your hand and a couple of questions that are there. We are here for you. Like I said, today is an easy, simple day to get you used to working in the building system if you have not worked in the building system before, and for a lot of you to put everything together. Just so you get a good indication of what's going on Thursday, we will be looking at the elevator system and the object management system. And what we'll probably do for theory is we're going to take you through a little bit of theory on the rack and pinion, a little bit of theory on the slides, and so on. Now, we know on Thursday that you may not get the full mechanism built simply because of the components that we put in it. But the idea would be to build the A-frame and to get some mechanism built that would be powered by either another motor or the servo motor. Okay, so that we can take you through the programming of that and the setup of that going forward. Our main control here was to build the base robot. All right, we'll do that on Thursday. Next week is where we're going to focus more on wiring and programming. This will include for a lot of people, just because some of the stuff that we've got on technical support calls and so on, the actual installation and setup of the software and how to get that working correctly first. We've done a little bit of work on simplifying the installer for you in the last couple of days. The reason for that is that some of the online stuff, Microsoft has changed some file locations, which has caused some problems. So we've actually got a share that we're going to make available to you that will allow you to get everything that you need unique for World Skills. And that's the important thing that you must remember, is that what we're providing to you in a package is what you need to use for World Skills. All right, there's other tools out there, but they won't be compatible with all of the libraries and so on for World Skills. So it can be easy for people to get a little bit confused. The other thing that we will do is we've just created a resource, a robotic share resource. And shortly what we'll do for day one is we'll put all of the files for day one there. The video that we talked about recording, we're only going to put up the first hour. So that's why we're going to edit it. And that little bit of presentation we'll put up on the Studica Robotics YouTube channel starting next week. Okay, so hopefully your builds are going well. We can't really see them because we didn't put everybody's camera on to spy on you. But if you have any questions, like I said, we're sitting here, we're live. and we're ready to support anybody that needs it. Okay, hi everybody. I hope you're still there. We get a few questions, so we thought we'd bring that up. There was a question in the chat because at one point in history, we had looked at the drive base that we have here, okay? And this is also a holonomic drive, three-wheel drive robot. When we did this drive base, we actually had mounted the wheels. Somebody asked, whoops, there go my batteries, in the center of the channel this way, okay? The question was, well, why don't you mount them that way? Why are you mounting them the way that we did before? And, you know, it can be a fairly simple answer. It was design preference, perhaps, okay? But one of the things that we get when we do it this way is we get a little bit of a different alignment where we can put other components in for it. And one of the big things about it is that if you look at your distances that you're going to use, we're at the same height between the robots, but we're actually widening out the base, okay? So when we mount it this way, you know, we have certain distances between it. We're narrowing the base. If the robot's gonna have a high elevator system on it, we want to even out that weight a little bit. So by mounting the wheels here in the corners this time, we actually get a little bit of a wider base, okay? Which will overall lower the center of gravity and improve the stability of the robot, all right? So that's one of the reasons that we did it that way. Coding is no difference. It's entirely up to you. There's lots of ways that you can do that when you're gonna put everything together, okay? So here we had them in the center on a sample base like this, right, when we drove it. And in this case, just a little bit of a different fundamental design, but you're gonna look at it and you're gonna see that I'm actually, you know, increasing, okay, the overall dimensions of the base. So I have a little bit better stability for what we wanna do in this system, right? The other way we could have put maybe smaller channel on, got a little bit more maneuverability, lots of different reasons to do that, but it's just a different design and we don't do everything the same way all the time. This is why we prototype and design and build different things. Okay. Nobody wants to give me a robot picture yet, so we can share it with everybody to see where they're at.
Yeah.
Okay, everybody, not a lot of questions. I hope everybody's building. We got one on our Discord. Feather Lemons, I like it. It's a good robot. I really like the bowling alley in the back as well. So a little bit different picture. He's building just a regular four-wheel drive robot. That's fine. That's no problem. Coding is coding. So as long as we get a robot base built, we'll get a project going on this next week, and we'll get that driving around. One point about that robot that I was going to bring up when we talked about the design of ours is that you have to remember that the VMX contains the IMU, or the integrated motion unit, okay? And the default orientation for that is flat, with the front of the robot being to where the Studica is on the case, all right? So if I stop my screen share when you're going to look through this, and this is great, you know, people try stuff and we get a little bit of interactive conversation going on here. Can you flip me over, James? Okay. James is flipping me over all right now. So when we mounted that robot, okay, this right here, this is the front of the robot because this is our lift mechanism right here. So the orientation of the IMU is the front is with the Studica logo at the front of the robot, which is why this is centered and in the flat. Okay, so if you're going to use that, the gyroscope or the accelerometer in the integrated motion unit, you need to remember that. When you mount this way, you change the default orientation. It's not a problem, but in your code, when you look at the libraries, you got to change that default orientation. Okay, and just be aware of that when you're looking at that. And we're going to put up a lot more resources. I sent out everybody a share to talk about that, the IMU and the default orientation. If you've been going through all of our video series, there was one that we did back in the summer where we talked about that, that orientation. So just looking at that robot, cool. And it just helps me now. So later on next week, we'll talk about that default orientation again. And coding for the gyroscope. We'll get some resources available for you. All right, excellent, cool robot. Surgery on this robot.
Hi everyone, hopefully you're still there. At the end of the day, you'll get an email, or Derek's already sent out the email. In that email, there's a SharePoint link. The SharePoint holds the files that we're working for the training robot. In each, in the file, you'll find the day one documents. So that's the stuff we worked on today. You'll also find the PowerPoint. There's a nice rendered image. There's some drive bases. There's a step file, the PDF. There's the document Derek was talking about the holonomic implementation. There's a BOM that Derek added. If we go to day 2, that's what we're doing on Thursday. You can see the A-frame, elevator, and OMS assembly. And then in the main folder, you can see the full training robot PDF file, and then there's the full training robot step file that you can download. Do note that the training robot, the main robot, is a very large file, and it could take a long time for your CAD software to open and implement everything. So I would open it overnight because it could take a while. All right. We'd also like to thank all of you for attending today, and hope to see you all on Thursday.
Yeah, we're going to be online because I know some people are still building when you're going to work through it. A couple of points. You want to go back to the small screen for me? All right. I'd left this up here with a little bit of a close-up of the way, just so that you could see it, that the motor mount, okay, the front motor mount goes into the 48 millimeter channel. All right, notice that the flat piece is on the top here, which doesn't have the 2 screws because they do not line up. They're not built in or aligned for the purpose here. They're used for something else that we're looking at designing for other mechanisms and so on. So when you put those in, you have your 4 button head screws, and your flat piece will be at the top of the opening, okay? So you can slide that in, and then once you've got that on, you can mount the wheel, okay, for your drive when you're going to do it. Please remember what I said about the wheel, okay? You're going to have to make sure that they're tight and they don't slip. And as your robot works, I mean, the wheels are going to wear. A lot depends on the surface that they're on. So you always want to check these and tighten these up anyways. So just, I would, create yourself a maintenance checklist at the end of each robot run or every hour, things that you want to check, and then just go through that. Because if you're like me, I'm aging and I forget a lot of things real easily. So I have a lot of lists. All right, which is good. So we'll be here if there's any more questions on that build. You have the files for Thursday. We're going to talk about the different mechanisms on Thursday. Thursday is going to be a busy day because it's going to take us a while to actually look at a mechanism like that and to build it. Okay. All right. You can always switch back already.
All right. Bye, everyone.
I'm going to